Okay. So let's look at 182. So what exactly is a rotation? A figure is rotated. How can you describe it? Investigate this question below. All right. So let's plot those points. You guys should know how to plot that. I could do that. So you could do it too. Okay, so 1 comma 4. Sorry, 4 comma 1 and 2 comma 5. Let me move that over a little more like that. Okay, this is A. This is B. And I'll connect them as well. Okay. Now, if I'm looking to rotate it counterclockwise about the origin, here's how we're going to want to think of it. It's a little funny. We're going to want to compare A to the origin. So notice I'm doing this dotted blue line from the origin to A. And I'll do likewise. I'll switch colors for a bit of contrast. I'll do a dotted green line from the origin to B. So in all likelihood, what I'm probably going to wind up doing is maintain that same distance on the other side after I do the rotation. But the best way to do the rotation is use your tracing paper. But notice how I added 2 more sides. Obviously, the dotted blue line and the dotted green line. So what I'm going to ask you guys to do is use your tracing paper. You guys know how to use tracing paper now. Put the pivot point at 0, 0. Trace the triangle that I have in pink, blue, and green. Rotate 90 counterclockwise. Your new triangle should be in the upper left quadrant. It's going to do a triangle, but just yeah, it's going to be a line. That's going to be easier. Actually, you know what? I think you're fine if you don't draw a triangle. I think you're still okay. If you just have the line AB, I think it'll still be okay. But I think what I'm more curious to know, where does A and B land in the upper left quadrant? By the way, quadrants are the sections of a quarter plane. You guys know what this quadrant is called, by the way? We call quadrant 1. Which one's 2? Yeah, 3, 4. You get it. So you guys are familiar with that. So I'll make sure. I don't know. I'm not sure when that's taught. Usually when I teach algebra 2, everyone knows. But so if you rotate it, where's A prime going to land? Good. It lands at -1, 4. Where does B prime land? Good. Thank you, Kira. So yeah, that's where it lands. So it's going to be at -5, 2 for B prime, and -1, 4 for A prime. So B prime. Now what's going to happen is that if I were to draw this, those 2 dashed green lines are the same distance if you were to actually measure it. And likewise with this dashed blue line. So essentially what it's done is we've done an angular investigation about the origin. And what we're noticing is that then X and Y switch for point A, then X and Y switch for point B. And at the same time, the sign of X went from positive to negative. So it's going to be a generalization we're going to talk about when it comes to rotations. And we're going to come with that generalization later in the class. But when you do a rotation, we're noticing that the X and Y values switch. They swap places or trade places, and then the sign of X went from positive to negative. Okay. Now, it says here, compare the lengths of and angles formed by the line segments that connect A, B, and A prime, B prime to the origin, which I did. Which lengths are equal? So I'll call this point O, by the way. So OA clearly equals OA prime. We expect that. Also, OB equals OB prime. We expect that. Now, what angles are the same? Well, probably AOB would be the same as A prime O prime, sorry, A prime O B prime. So angle AOB I would say would probably be the same. Wait, hold on a sec. Oh, never mind. Let me back up a little bit here. Let me back up, guys. I see what's going on now. So this is why I do a better job on E period than you guys. So, but it's okay. I'm learning at the same time. Um, let's focus on AO prime. AO, sorry, AO A prime. It's a lot of letters and times. AO A prime. Notice how AO is blue and OA prime is blue. What do you think the measure is going to be of AO A prime? Okay, what do you think? Yes, it's right angle. And why should it be 90? Because then we just rotate 90? Yeah, then I just take that and rotate 90? Yeah, that makes sense. Yeah, that should be 90. Yeah, okay. That makes sense. I'm cool with that. What else would also be 90 degrees? BOB prime, yeah. Because that green line also rotated 90 degrees. It's kind of cool. So therefore, I can conclude that angle AOA prime is the same as angle BOB prime. You're good?
Wait, what's that thing like after 90 degrees?
It's an and symbol. Yeah, my handwriting sucks. I apologize. Thank you for clarifying. And there we go. An and symbol. Okay. Yeah, that makes does that make sense? Like those two dashed green lines are 90, two dashed blue lines are 90. Okay, cool. To help you, may want to draw line segments connected. That's why I did it. Okay. All right. Now, part D says use trace paper to help see that a rotation does not change in angles or lengths of a figure. Note that this kind of transformation is called a rigid transformation. Name the rigid transformation that you know. Well, we already did the tracing paper, so I don't think we need to do that. But let's list the rigid. So rigid, first of all, let's just forget about math class. Let's say it's like English class, we're doing a vocabulary quiz. What does word rigid mean in general? Not, yeah, or not willing to bend. Or what if your parents are very rigid with you? Or a teacher's very rigid with you, or your coach is very rigid with you? What does that mean? Strict. Yeah, they're not going to bend. Like, you gotta be home at this time. You gotta be practice time. You gotta turn your homework this day. So like you're not flexible. And that's what's happening here from a geometric perspective, is that these triangles don't change. They keep the same size and shape. So when something is rigid, we expect the same size and shape. Now, what are some examples of rigid transformation we've done already? So again, rigid transformation, same size and shape. Or if you have a very rigid diet, like every day I just eat yogurt and a banana. That's boring. You gotta mix it up sometimes. But just it's all the same. So what are the rigid transformations we know? We definitely know translation. Because if you move things left and right, does that change the shape? No, right? Who cares? Move up and down, left, right, it doesn't matter. Remember, if translation is like up, down, left, right, it's all the same. Reflection, you just flip it over, big deal. Doesn't change anything. Just how it's pointing. Remember, what's a reflection? It's a flip. And lastly, rotation. So these are called rigid transformations. Connor, go ahead. Yes, what do you think the non-rigid one would be? Yeah, stretching or compressing, which I don't think we do in this unit. If I'm not mistaken. I'm not sure. But that would be so yeah, actually let me just make a quick comment about that. Non-rigid is when you stretch or compress. In order to do that mathematically, you're gonna have to multiply the x or y coordinates by a number to make that happen. But I don't think we're doing that today. Okay, so give my voice a little bit of break.
Sabine, can you read note 183, please? Keep going.
The result of translating
Mhm.
angle ABC. How much information is necessary to describe the transformation? Describe the transformation as efficiently as possible. Most of them involving is.
So thanks, Sabine. So let me give you a model to follow. What you definitely need, you need the coordinates of 1 point on the original diagram and the coordinates of the corresponding point on the new diagram. That's what you need. Because otherwise I don't know how it's going to change. I definitely need that.
Right, like, so for example. Notice the C given to me, right, the original -1, 4. Is that corresponding point provided on the new diagram? It is. Are the corresponding points given for A prime, B prime? No, but it's okay. If, as long as you give me the coordinates of 1 point on the original and the coordinates of, I really emphasize this word,
Corresponding. So, for example, what if you're not given these? Just being hypothetical, and not given that either. But you're given this, which is what? 4, 5, I think. I mean, obviously I can tell what B and A are by the diagram, but what if I didn't even give you a coordinate point? What if I just didn't give you an image? I just gave you the coordinates as text. Said, oh, point A is here and point C is there and point B prime's there. That doesn't help me, right? But if I gave you what C and C prime were, then I could plot it. Now I think I'm okay. I think I can do the transformation. Because then I know that, oh, C went from here to there. So you definitely need that. So now let's go ahead and describe it. If I describe it, let me get rid of the other stuff here. There's lots going on. But yeah, clearly I have everything I need. So really our focus is going to be on C and C prime. That should be our primary focus. So what happens? How do I go from what to what? I went from -1, 4 arrow to 6, 1. So what happened to X? The add or subtract to go from -1 to 6. How much? So you're going to say 7 right. And what else? 1 from 4 to 1.
3.
3 down. You could also write like this. X plus 7 and Y minus 3. Because that is what we're doing. We're consistently going to be adding 7 to X and subtracting 3 to Y. So you can write like that as well. So that's how we state our transformations. We state it this way. Should be pretty intuitive. Just look at it, right? So that means I apply that same transformation to all the other points.
So now I know what A and B are. Guess what we do? Add 7 to X, subtract 2 to Y. So that should be 3, 3, makes sense. That should be 4, 5, which I already said so. So, yeah.
Okay. Makes sense? Pretty straightforward. Okay, cool. Let's go on to part B now. I think you guys could probably try part B on your own. And maybe C and D. So let's read it first, make sure we know what we're doing. And then I'll walk around and help you guys out. Let's see, Peter, can you read part B, please? Mm-hmm. Mm-hmm. Okay. Correct. Okay, perfect. Why don't you guys in your table groups do B, C, D? You guys could totally handle part B. You're doing the same exact transformation as we did in part A, which means I'm going to add 7 to X and subtract Y by 3. You can do X plus 7 and Y minus 3. So plot those points, get the new points, and go through C and D, answer those questions. You guys should be able to answer those questions just fine after the discussion we just had. I'll check in about 2 or 3 minutes, see how you guys are doing, and then we can wrap up these notes and start the next set of notes. And I'm gonna do it myself, walk around and make sure you guys are doing okay. The one's a little off the graph, just be okay with it. I got these fancy colors. I might look more fancy to you guys. Oh, hold on, Lucas, one sec. I'm sorry, say again? We're not rotating. Yeah, we're just moving left and right. We're up, down. Hold on, LA. I'll be out there in a sec. Okay, I'll come around and see how you guys doing.
Oh, yeah, yes, go ahead. Yes, look, yeah, but it's like. No, which one is my site? The first one, right? So we're doing the same thing as we did in Friday. What do we do in Friday? X plus 7, Y plus 2. So you have to, so then also you do. Way to Ryan. Well, that's wait, just then. No, that's just a new location, that's all. It so happened to be the location for one of the farms. Yeah, for 182, but for this one, we're just sliding. So that's all we want to do. So now, it's supposed to back to 5 times. At 17. Yeah, guys, you're just adding 7x, subtracting Y by 3. Yeah, good. Perfect. Good, got it. Good. Yeah, good. You got it. Yeah, that's so then let's make a comment about it for part C. So you got part B done. So for part C, what's happening was that you do these little connections. Each of these oh, I see where it is a little lost. So you want to connect this with this, this with this, and this with this. Correct. Yeah, they're all parallel and they're all the same length. Guys, once you have it done, you want to correct.
Yeah, and then connect the fourth one once that, and like. Boom, 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 and stuff. That's good. Okay, cool,
Oh,
good. Kind of looks like a three-dimensional object been created. They're also going to be moved, you move each thing. Okay, let's say you guys are ready to see the results. Oh, please. Okay, here we go. Yeah, so here's what's happening. So I got nicer colors, but it's okay. So I got this neon green that I did an original, I got the brown that I did the transformed. So I went 7 right, 3 down for every single point. Then I connected the corresponding points using my nice colors, my dash purple. And those dash purples are all the same. They're all the same, and they're all parallel. So that's what Parks is asking you, what happens when you connect the corresponding points? Gets line segments are all the same parallel. And why should that be true? Because we translate the same distance, the same direction. That's why. And then for part D, yes, it is rigid, because we do not change that brown triangle is the same shape as that green triangle. It did not get stretched or compressed in any way. It maintains the same shape and size. So there's no proportion, everything's the same, but really everything's just identical, just in a new location. That's it. So now you've hopefully got a better understanding of a translation, moving left, right, up, down. You can call it a slide if you want to call it that. You're sliding. Questions at all? We good? Okay. I'll go and freeze that for a moment while I queue up the next part. So the last part of the notes before we move on to the next set of notes. This one's going to be about facts about isosceles triangles. How can transformations such as reflections help us to learn more about familiar shapes? William, can you read that part about 184? Yeah.
Facts about isosceles triangles. How can transformations such as reflections help us to learn more about familiar shapes? Consider reflecting a line segment, a portion of the line between 2 points, across the line that passes through one of its endpoints. An example of this would be reflecting across in the picture outright.
Okay, so let me show what's happening with this one. And are you guys okay? Can I clear this now?
Yeah.
Okay, cool. All right, so let's go ahead and do that. So what I'm doing here is take a look at connecting this with this. So our goal is to flip point A over line BC. So I flip it over, wouldn't it just be over here? Right? So if I think about it, these would be the same length, right? AC would equal A prime C. Well, if that's happening, I probably would expect those to be the same. I probably expect AB So what have I formed now? I formed a triangle. But it's a special triangle. A triangle which, how many sides are the same? 2. Now, if all 3 are the same, call it equilateral. But that's not true. I mean, at least I don't think so. So I don't know. Well, actually, it's not going to be because it's definitely that shorter than AB. But yeah, it's isosceles, right? So that's what we've generated. So yeah, clearly we see that AB equals A prime B. So when you look here, it says copy AB and draw A prime B, the reflection of AB when points A and A prime are connected. What figure is formed? So we call this an isosceles. Triangle. And that's because you have 2 congruent sides. And my two congruent sides are those right there. Those are my two congruent sides. Also, another observation we can make is that angle BA prime is congruent to angle BA prime A. So these two angles the orange ones are the same. By the way, I kind of made a little mistake here. I said AC equals A prime C. That is true. There's nothing wrong with that. But C was not that middle dot. So let's give that another. Let's put another dot. Let's give that another label. Let's call that point D. And I'll change that to D. I mean, it's true. AC does equal A prime C. That is true. That was not false. It's just a little confusing if you guys are a little confused. I meant to say that. What the? Two sides. I crossed my Z's. Yeah, because I'm hammering is not great. Yeah, two congruent sides. It's two. Actually, we'll just write the word two. Yeah, please clarify. I won't be offended. My fault when I was like 6 years old, I didn't take handwriting seriously. I'm very conscious about my kids that they have to have good handwriting. They practice every day. So, all right. Let's look at part B really fast. Use what you know about reflection to make as many statements as you can about the shape from part A. For example, are the any sides that must be the same length? Are there angles that must be equal? Blah, blah, blah. Well, I think what I'm noticing is that BC cuts A prime in half. Would you guys agree with that? Yeah, I'd agree with that. So cuts in half. Also, I probably would say BC is perpendicular to A prime. And actually, I should draw this as a segment to be proper. Yeah, I'd say that. You guys know that symbols? Perpendicular. Yeah, perpendicular. Yeah, just because I want to wrap words. So whenever you see that, great question, Reagan, because we want to get used to symbolic. And sorry if I had assumed that, but yeah, it means perpendicular. Right. That's all. So, and by the way, do you guys know the symbol for parallel? Two lines of parallel? Two lines, exactly. You kind of slanted a little bit, yeah. Feel like that, I guess that works. I don't know. But yeah, they're perpendicular. So what you're doing is you're forming. Actually, we actually call this kind of lends itself well to something we'll do later in the year. Okay, I'm gonna write this out. It's called a perpendicular bisector. And a lot of people get confused by this because it sounds so fancy with perpendicular bisector. Ooh, look at you. But no, it's just all you're doing is that you're what's that? All you're doing is you're stating that hey, this line BC cuts A prime in half and it's perpendicular at the same time. Those two things. Or right angle and cuts it half. So okay. So I think we're pretty thorough with those notes. Seems okay. Okay, cool. Okay, so we go to 1.2.6. We do have to do a set of notes. We got plenty of time. We're okay. Yeah, we're still fine. So we got another 40 minutes, I know. Long classes, I know. But the hope is we get this done about 15 or so or 20 minutes, and then we can work on homework. All right, so 1.2.6. I hope so. That's a hope. Find out. Sure, go ahead, yeah. All right. So we're doing more reflection. We're just gonna have make some comments about these. And then we have some algebra on the next page. Okay. Or page 3. Again, just give my voice a little break here. Lucas, can you read 199?
This quote design has reflection symmetry, because if the design were reflected across the line of symmetry, the image would be exactly the same as the original design. That is, the figure has reflection symmetry, if the reflection carries it off of itself. Um, Obtain the lesson 1.2.6 research page. On it, examine the many shapes that will be the focus of the course. Which of these shapes are reflection symmetry? Consider this as you get to the question below.
Okay, so you guys have that in front of you. You guys have this like extra sheet here. I kind of goofed and didn't copy. So let me find one right now. Well, we're gonna go through this. We're gonna spend some time really sitting on this. And we're gonna answer these questions about symmetry. But let me locate it because I should have done that. Let's see here. I think I should be able to pull it pretty fast. Hopefully. Ah, look at that. Okay. Thank it's Mr. Davidson that he's on top of this stuff. And there we go. Love the technology. All right. Yeah, so let's kind of rest on this a little bit. So the question is asking us,
But I don't know where mine just went. You have another one?
sure. I got plenty.
No, it's a ghost of people. Black faces, yes. Yeah. All right, so anyhow, so let's look at this here. For each figure on the resource page, draw all possible lines of symmetry. If you're not sure, if the figure has as much symmetry, use tracing here, blah, blah, blah. Okay, so, actually, I'll kind of do this on my device.
We use red lines. Okay, so I would say that would be a line of symmetry, right? Would you agree?
Yeah.
That would be a line of symmetry. That would be a line of symmetry. There's none here. But let's take a look at oh yeah, we got more. Do you want to tell us more? Yep. Likewise with the kite. No, yeah. Well, no, I can't do the kite. I lied. I can't. Nope. But the rectangle I can. So what you want to do is if you like actually got some scissors, cut out a square piece of each of the shapes and fold along the red or green lines, they would map onto each other. You'd want that. Does the hexagon have more? Yeah, diagonally. 100%. Oh, that was off. Try it again. Okay. Yeah, so I would say there are probably 4 lines of symmetry for the hexagon. Chi has 1, rectangle has 2, scaling has none. Go and try the other 8. Do your best to state how many there are. Actually, there might be more for the hexagon. I just realized. Do we have more? Connor, you have more? Yeah, there's more for the hexagon.
Every flat side.
Yeah, because I did it earlier for, yeah. Running out of colors here. Yeah, I would agree. So 6. Here is 1, and here is 2. Okay. So go and try the other 8. I'm going to do it also, and we'll compare in a moment. All right, here's what I got. Keep going, I got 3. Yeah, sure, go ahead. Square at 4. Rhombus at like a diamond at 2. Quadrilateral, all the sides are different, that'd be 9. Isosceles triangle, 1 each. A trapezoid, unless these 2 sides are the same. I don't know that. Now, circle, I said infinite. Because I could draw so many ways. Hopefully you guys might see a pattern. Focus on the hexagon, the triangle, and the square. What connection are you seeing with the lines of symmetry and the number of corners? Do the number of corners equal the number of lines of symmetry?
Yes.
Yeah, assuming that all sides are the same, right? So even though triangle, all sides are the same, I have 3 lines of symmetry. Square, 4 sides the same, 4 lines of symmetry. Regular, I emphasize the word regular, when all the sides are the same, all the triangles are the same. 6 sides, those 6 corners, I have 6 lines of symmetry. Now a circle, if you think about it, it's kind of like a polygon. It just happens that you want to have an infinite amount of sides. If you actually increase the hexagon to like maybe 20 sides or 30 sides or 40 sides, what if it's a 60 sides? It's gonna look pretty darn close to a circle. So as we make the number of sides infinite, we're gonna have infinite amount of lines of symmetry. A circle, there's so many I could draw. I mean, it's all over the place. I could do this, 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 I could do this. It's getting crazy now. So if that makes sense, we're cool with that? Okay. So now we can answer the question on the next page. Go and answer those questions on B, C, D. Oh, there's 4 more? Oh my gosh. I didn't realize. Oh my goodness. So much work. Okay. I would say none. I'd say 1 here. I said that earlier. It would be none again. Because even if you did this, it's not a reflection. It's not going to map onto each other. Pentagon, 1, 2, 3, 4, 5. Okay, now I think we're ready to answer the question on back in the notes. So go and try BCD. I'll show you the answer key in a moment. Try BCD. And then we'll move on to rotation symmetry after that. So yeah, go and do 199 BCD. What are you guys saying for part B? What type of triangles? And isosceles also. And isosceles. Yeah. And then which of the quadrilaterals, the 4-sided polygons, had reflection symmetry? Definitely rectangle. Definitely square. Definitely kite. Rhombus, definitely. And probably isosceles. Yep. And which one had more than 3 lines of symmetry? Yep, you guys got it. Here we go. Yep. Yep, that makes sense. So square, rectangle, rhombus, kite, isosceles would have of the polygons, or the the quadrilaterals of 4-sided polygons have reflection symmetry. And that's mainly because we're having at least 1 pair of congruent sides. Also, you do have congruent angles too. For a kite, 2 angles opposite of each other will be same. The angle that's formed between the non-congruent sides. More than 3 lines of symmetry, yeah, square, regular, pentagon, red hexagon, circle, saw that. That's because you have more than 4 sides where angles are the same. So, okay. We're cool with that. All right, so now move on to this one here. This one I'm gonna have to kind of do with you because it actually does require accessing a site. But let's talk about this one here. Let's see. Cam, can you read 100, please?
Similarly, some figures can also be rotated onto themselves so that they example diagram of it. When this figure be rotated onto itself, place the shape on facing figure and use the on the is it possible there can a rotation?
So don't we won't do on the tracing paper. I think we'll just rotate it. So it's kind of cool. So right now, let me go back to the original. So right now I haven't done a rotation, right? Okay. How many degrees do you think I have to rotate this to get back to the same place? What do you guys think? Well, definitely 360 for sure, but are there some other angles less than 360? I will go 120 instead of 90 because if you go 90, here's a problem 90. What's 360 divided by 4? 90, right? But how many not sides, but how many different things? Yeah, so if I do 360 divided by 3, I would get 120. So if I go 120, okay, still not there yet. Almost there. Boom. And then if I keep going, when is it gonna hit it again? Yeah, which is another 120 away from 120. Yeah, and then do it again. 360. So what we're noticing is that because I had like 3 sides or 3 features, the symmetry was divided by 3. If it was like a 5-sided, then of course it would have been 72 degrees by the way. So that's what we're noticing here. So let me share the comments with you guys. So yeah, it's just easier. I did a demonstration instead of you guys using trace paper. So let's talk about the what the Ansky says here. So it says here this figure can be rotated twice, 120 or 240. The point of rotation is in the middle where the lines meet. That's true. And Jessica claims that she can rotate all figures such a way that that they will not change. How does she do it? She rotates 360 at any point. Yeah, always if you rotate 360, you always get back to the same place. We know that for sure. That's always gonna be, if I did something really strange, like what if it wasn't symmetrical or whatever? Like I don't know. I just made some weird object. If I rotate this 360, of course I get back to the same place, right? But this does that have any of this rotation symmetry? No. Because these are all different, right? They're like different angles and shapes and what's lengths. But these are all identical, right? Like this right here, this spiral is the same as this. Like if you actually were to manufacture this, you just manufacture, multiple of these and then just connect them. They connect in such a way where this is going to be 120 degrees, 120 degrees, 120. And of course, as you go around the whole circle, 120, 120, 120, how many degrees is that only gone around once? 360. So what you have to do is you have to take the number of identical portions, if that makes sense, and do 360 divide by that. That's how you can tell. So that's why 120 would make sense. And then of course, you keep doing 120 over and over again. And 120 is a factor of 360, right? Or 360 is a multiple of 120, multiple of 3, right? Okay, so that makes sense for that one. Okay, now that you know about this, try part C and D. Using your reference sheet again, which ones have rotation symmetry? So part C is asking you, which ones have any kind of rotation symmetry? And then part D is specifically asking 90-degree rotation symmetry. So go and try part C and D now. I'll show the answer in a moment. Yep, here we go. So go and try part C and D. Now you understand what rotation symmetry means. Give it a try. So I'll pull the reference sheet as well. So kind of help you guys out a little bit. So now, obviously, all these will have 360 rotation symmetry, right? All of them do. But are there any of those where if I do less than 360, I can get back to the same orientation? Definitely here I can. In fact, actually, what will be the exact angle I can rotate this to get back to the same place?
40. No,
Well, what's 365 by 6?
50.
If I rotate 60 degrees, I get back to the same place. So I go 60, 120, 180, 240, 300, 360. Would a kite have that? No,
Mm-mm.
you have to rotate. Rectangle, no. Definitely not scaling. No. How do we call a triangle? Yeah, and actually rotate 120, you would you keep getting that. How square? Yep. Isosceles, no. Circle, yeah, for sure. Rhombus, no, because not all the angles are the same. Quadrado, no. Isosceles triangle, no. So it's gonna have, actually, wait, the rhombus, it can. It's 180. I lied. And actually, rectangle, I lied also. I lied to you guys. Wrong. Okay, see, that's why I do better with my E period. E period, like, I'm assuming you're over your notes well. Let's consider. Ah, my bad. Rectangle's 180 symmetry. You rotate 180, get back to the same place. If I label the points, and like it was a rhombus, that's also 180. Yeah, my apologies. Definitely does have that symmetry. A parallelogram does as well. Actually, there's still 4 more. I didn't realize it. Regular pentagon, yes. But scalar right triangle, no. Isosceles triangle, no. The parallelogram, actually, if I rotate 180, I will get back to the same place. So let me show you the notes. Here we go. Yeah. So again, since all figures can be rotated 360 without change, this is not a very special quality. Like what they do, fine, they're all 360. But some are special where they can be rotated less than 360 and still remain unchanged, be in the same orientation as it was before. Regular hexagon, rectangle, equal a triangle, square, and I'll even kind of tell you the specific angles you could do. Meg, go ahead. Yeah, you're in the same configuration as you were before. If you were to like label the points and then rotate it in such a way where, okay, the points are in different positions, but it's still the same shape or still the same configuration. Oh, it depends. It depends. For a rectangle and a rhombus and a parallelogram, those are 180. For square is 90. Equilateral triangle is 120. Regular hexagon 60. Regular pentagon would be 72 degrees. So like pentagon, if I were to, I find it. Yeah.
What would be the box or a square if it's like a square that's kind of like upside down with a diamond?
Yeah, but a rhombus, okay, well, we'll get to rhombus in a moment, but for a pentagon, if I cut this out and spun it, like let's say it calls A, B, C, D, E. So I spin it, so now C's up here. So C's here, D's here, A's here, D's here, D's here. It's still gonna be the same configuration, right? If I rotate 72 degrees, I'll get this. And I keep going 72. Here's why I did 72, 365 by 572. Now for a rhombus, that's like a diamond. So all these sides are the same. The problem is that this angle is not the same as that angle. That's why it's only 180. So if I rotate 180, I get back to the same configuration. But
Just like all the tables.
oh, then that's square.
Oh.
That's square at that point. But if the all angles are the same, not all the sides are the same, you have rectangle, still back to 180. So square is a little more special. And then which one has 90-degree rotation? Only a circle. The circle rotate 90. Yeah. Because for rotate a circle, like even 0.1 degrees, still the same thing. The square, of course, you have to rotate 90. Okay. Let's move on. Let's keep moving. We're almost done here. Let's talk about this stuff. Now let's go all types of symmetry. So we're gonna put all together. Reflection, rotation, yeah. actually, those are only two we're talking about. So anyhow, now describe all types of symmetry for the same figure possible. For example, let's say you have 10 sides and it's regular. So all sides are the same. So it's a decagon. What reflections carry this decagon unto itself? Does that describe its lines of reflections? If the polygon has no reflection symmetry, explain how you know. So how many lines of symmetry can I draw for this one? There we go. 1, 2, 3. Notice I'm trying to go in order 4, 5. Switch colors. 6, 7, 8, 9, 10. 10, and essentially what you're doing is you're connecting hopefully that makes sense with my comment. Yeah, you're connecting opposite points and opposite sides. You have 5 pairs. A pair is 2, so you have 5 pairs, that's 10 points. 5 pairs opposite sides, 5 pairs, that's 10, so you got 10 sides. And that's what we're doing. That's why I have 10 lines of symmetry. And it looks a little messy there. So what rotations carry this polygon to itself? So we could rotate 10 times. Or how many degrees? 36. Thank you so much. Yeah, because you do 360 degrees. Divide by 10. So 36 degrees. Yeah, just rotate 36. You're always going to get back to itself. Okay. So let's talk about the last page, and then we're done with the notes. I'm just trying to understand the last page. Any questions on this so far? We're good? All right. Okay, last page. I'm just trying to understand it. Okay, so during this lesson, you have focus on types of symmetry that can exist in geometric objects, but what about shapes that are created on graphs? What types of graphs have symmetry? So examine the graphs below, decide which have reflection symmetry, rotation symmetry, or translation symmetry, or a combination of these. So translation means if you move it left and right, or up and down, or diagonally, you can get back to the same place. The line is kind of an interesting one. It's kind of interesting. I'll do the line with, I'll do part 8. I'll do the line because that one's kind of weird. I'll have you guys try the other ones. And we'll have a discussion. So, for example, I could move. So this dot here, hold on. We'll do a dot 0, 1. What if I went 1 up and 1 right? If I go 1 up and 1 right, am I back to the same place? Yeah, 1 up, 1 right. So it doesn't really matter if I went to the left or to the right. Essentially, if I'm using my slope. So this has translation symmetry. I'll call it a T for translation. So I'll call it translation T. Actually, that's confusing because R is the same letter. That's right. Yeah, so this definitely has translation symmetry. What that means is that if I took a point and moved it to the left and moved it up or down or whatever, can I get back to the same place? The answer is yes, I can. Can I rotate it about the middle and get back to the same place? Yeah, I could rotate 180. Yep, so that's definitely has rotation. In fact, it's 180 degrees. Just take a pivot point, any point really for that matter, because lines go on forever, and rotate 180, get back to the same place. What if I kind of reflect about a line that's perpendicular to it and still get back to the same thing? Yeah, I can. Yeah, if I took a dash line here, reflected every point along across that, yeah. Yeah. So it has reflection symmetry also. Yep. So it has translation, rotation, and reflection. It's a little confusing, especially the translation part, because you have to realize that if you took a point on the line and you did a very specific translation, like up this much, right this much, that slope basically, you will get back to the same place. Now take a look at the parabola, the one to the right. If I rotated it less than 360, can I get back to this, or does it kind of only rotate 360 to get back? Yeah, only 360. Yeah, so that's how you can tell if you could rotate less than 360 and get back to the same place. So I'm gonna say no rotation with that one, but can I cut it in half? Can I reflect it? Yeah, yeah. This definitely has reflection, so I could go down the y-axis. But once I start moving it to the left or to the right, I'm never gonna get back to the same place. You know, once I start moving around, forget it. So the proud just has reflection. Let's take a look at this curve. This is called a sine curve. Can I rotate 180 about the origin and get back to the same place? Yeah, you can. Yep. I could definitely translate it because see the peak kind of repeats in the same place. It's a pattern. I could definitely translate and still get back to the same place. I could slide it and still be in the same orientation. And I could reflect it. It's a little bit confusing. Actually, yeah, you can always, yeah, you don't have to use the y-axis. I can always reflect it like this, and it gets back to the same place. So it has reflection as well. You just draw a line through any peak or trough, so that could reflect. Okay, go and try the last three. See how you guys do, and B and C, and then we're done with the notes. Excuse me. So lower left, what do you guys think? Yeah, you totally choose green. Yeah. Could you have your reflection like this?
Yeah.
Yep. And you can rotate it. So reflect and rotate. Can't really translate that one though. It won't get back to the same. What about the middle one on the bottom? Yeah, you can just translate. You can move it like diagonally, but that's all. You can translate it. Yeah, you could just reflect. Just like the parabola. Right. So part B, if the y-axis aligns symmetry, then its function is referred to as even. Which one are even functions? Definitely so which ones are even? That one and that one. We call those even functions when they when they have a line symmetry about the y-axis. And odd is those that have a rotation symmetry. So we call this one odd and that one odd. That's more specifically when they have a 180 degree rotation. We call it an odd function. Interesting, I'm actually doing this in my pre-calc BC honors class right now. We're talking about the set. But more from a function perspective, anyway. Okay, so that's good. We're all done. So good. I'm very happy got this, and definitely took a little longer than I thought, but the 75-minute period helped. If anyone wants a copy of the homework, I can give you a copy of it. You think it's gonna help? Yeah. Like her too, yeah. So, yeah, or their computer. With this for, yeah. But I'm sorry, that's what we got. Most bad.
Wait, what's going on?
Yes, everything on here is everything I like kind of face some problems here. So it's basically 113 to 116. And then 123 and 127. You probably get a head start. We only got about 8 minutes, but yeah, head start. Sure, yeah, sorry, everyone here. You want to, Meg? Sure, okay.
Yeah, I have a question.
If it goes, yeah.
Why is it, the like, Ruby one,
One,
the third, like, why is it?
the sign, yeah, that's the sign. Go ahead.
Why is that not?
Oh, that's because the wax doesn't cut in half. You want the wax, so if you cut a square piece of paper and pull along the y-axis, this would not map on, they would not map on.
Okay, sorry.
Yeah, the one that does do that. You'll learn about this in Melbourne too. It doesn't. Exactly, correct, right,
Okay.
so you have that symmetry,
So it's,
the wax is cut in half.
basically, like, if we could pull it out,
Yeah, like if I do this right now,
how about this?
no, because yeah,
Oh, yeah, I
that,
can do
yeah,
that.
yeah, not that, usually, that, yes. Well. We're gonna get 15 minutes for lunch today. Awesome.